At its core, paper is a highly engineered, interlocking web of microscopic plant fibers. The fundamental building block of this material is cellulose, a complex carbohydrate that forms the cell walls of green plants. In a living tree, these cellulose fibers act as hollow microscopic tubes, transporting water and providing incredible structural rigidity. However, within the wood, these strong cellulose fibers are bound tightly together by a complex organic polymer called lignin, which acts like a natural waterproof glue. The entire mechanical and chemical process of papermaking is dedicated to tearing this natural composite apart, removing the lignin glue, isolating the pure cellulose fibers, and forcing them to weave back together into a perfectly flat, uniform sheet. The journey begins when harvested logs arrive at the mill and are loaded into a massive debarking drum. This is a massive, slowly rotating steel cylinder, often measuring over 80 feet long, with angled steel slots lining its interior. As the drum turns, the logs tumble over one another in a chaotic, deafening cascade. The sheer mechanical friction of bark grinding against bark, combined with the heavy impacts of the tumbling wood, strips the outer layer from the logs. Bark contains very few usable fibers and is full of dark pigments and dirt that would ruin the final product, so it must be completely removed. Once stripped bare, the logs slide onto a conveyor that feeds them into the chipper. The chipper is a massive steel disc, sometimes 10 feet in diameter, spinning at hundreds of revolutions per minute. Embedded in the face of this disc are heavy steel knives. As the logs hit the spinning disc, the knives shear the wood against a stationary steel anvil at a precise angle. The physics of this cutting action is designed not just to chop the wood, but to pull the log forward automatically while slicing it into small, uniform chips. The size of these chips is tightly controlled, usually around 1 inch square and a 1/4 inch thick. If the chips are too thick, the chemicals in the next stage will not penetrate to their core. If they are too small, the actual cellulose fibers inside the wood will be cut, permanently weakening the final paper. The raw wood chips are then transported to the digester, a towering vertical pressure vessel that acts like a massive industrial pressure cooker. This is the heart of the chemical pulping process. The chips are continuously fed into the top of the vessel, along with a highly caustic chemical mixture known as white liquor, which is primarily a solution of sodium hydroxide and sodium sulfide. Inside the digester, the mixture is subjected to intense heat and immense steam pressure. Over the course of several hours, as the chips slowly migrate down the length of the towering vessel, the hot chemicals penetrate the wood structure and react with the lignin. The white liquor breaks the complex chemical bonds of the lignin, dissolving it into a liquid state while leaving the tough cellulose fibers intact. By the time the chips reach the bottom of the digester, they are soft and spongy. They are then expelled into a blow tank. As they pass through a narrow valve into this lower pressure environment, the sudden, violent drop in pressure causes the trapped steam inside the cooked wood chips to instantly expand. This rapid expansion literally blows the chips apart, separating them into a thick, dark slurry of individual microscopic fibers. This material is now officially called pulp. At this stage, the pulp is brown because it is still surrounded by the dissolved lignin and spent chemicals, a dark fluid known as black liquor. To recover the valuable cellulose, the slurry is pumped through a series of rotary vacuum washers. Massive wire mesh drums rotate through vats of the brown pulp. A vacuum applied to the inside of the drum sucks the liquid through the mesh, trapping the solid fibers on the outside in a thick mat. High-pressure water showers spray the rotating mat, washing the remaining black liquor away. The clean pulp is then passed through centrifugal screens. Inside these cylindrical machines, rapidly spinning rotors create strong fluid vortices. The good individual fibers are small enough to pass through microscopic slots in the screen basket, while any uncooked knots or large bundles of wood are flung outward by centrifugal force and rejected. To transform this natural brown pulp into pristine white paper, it must go through a multi-stage bleaching process. Bleaching does not simply paint the fibers white, it fundamentally alters the molecular structure of any remaining trace lignin. The pulp is pumped through a series of reaction towers where it is mixed with bleeding agents like chlorine dioxide, hydrogen peroxide, and oxygen. These chemicals aggressively oxidize the dark compounds, breaking their light-absorbing chemical bonds. By altering the electron structures of these molecules, they lose their ability to absorb visible light. Instead, they reflect all wavelengths of light, making the fibers appear brilliantly white to the human eye. Once washed and bleached, the pulp undergoes one of the most critical mechanical treatments in the entire process: refining. The individual cellulose fibers are currently smooth and tubular. If you were to dry them right now, they would not stick together, resulting in a weak, crumbly sheet. To make strong paper, the fibers are pumped into a conical or disc refiner. Inside, a heavy steel rotor spins just fractions of a millimeter away from a stationary stator. Both the rotor and stator are covered in hundreds of raised metal bars. As the pulp is forced through this microscopic gap, the fibers undergo intense shear forces. They are crushed, bent, and stretched by the passing bars. This violent mechanical action begins to fray the outer walls of the cellulose fibers, peeling back microscopic strands called fibrils. This process, known as fibrillation, makes the fibers look remarkably like hairy, frayed ropes under a microscope. This massive increase in surface area exposes countless hydroxyl groups on the cellulose molecules, prepping them for the complex chemistry that gives paper its strength. The highly refined pulp is then sent to the stock preparation area, where it is aggressively diluted with water. By the time the mixture is ready for the paper machine, it is over 99% water and less than 1% actual fiber. This extreme dilution is absolutely necessary to keep the microscopic fibers completely suspended. If the mixture were any thicker, the fibrillated fibers would immediately tangle and clump into knots, resulting in lumpy, uneven paper. This watery suspension is pumped into the headbox, a highly pressurized chamber that marks the beginning of the wet end of the paper machine. The headbox spans the entire width of the machine, which can be over 30 feet wide. Its job is to take the turbulent flow from the pumps and transform it into a perfectly smooth, uniform curtain of water and fiber. At the bottom of the headbox is a narrow, adjustable slit called the slice lip. A powerful jet of the dilute pulp mixture shoots out of the slice lip and lands onto the forming fabric, traditionally called the wire. The wire is a continuous, rapidly moving belt of tightly woven plastic mesh. The fluid dynamics at this exact point are critical. The speed of the jet exiting the slice must precisely match the forward speed of the moving wire, which can be traveling at over 60 miles per hour. If the jet is moving too slowly, the wire drags the fibers, stretching them out and breaking the formation. If the jet is moving too fast, the fluid piles up on the wire, causing chaotic turbulence and a cloudy, irregular sheet. The moment the jet hits the wire, gravity begins pulling the water down through the microscopic holes in the plastic mesh. The solid fibers, too large to pass through, remain trapped on the top surface. However, gravity alone is not fast enough. Underneath the moving wire are dozens of angled ceramic blades called hydrofoils. As the wire drags the water over these stationary blades, the fluid accelerates, creating a localized drop in pressure. This tiny vacuum literally sucks the water down through the mesh, locking the fibers in place. Because the fibers are long and thin, the forward motion of the fluid tends to align them in the direction the machine is running, known as the machine direction. As the water drains, the fibers begin to physically intertwine, forming a continuous, wet, fragile web. By the time the web reaches the end of the wire, it has transformed from a liquid puddle into a solid, albeit sodden, sheet of paper, roughly 20% solid fiber and 80% water. To remove more water without destroying the delicate structure, the continuous sheet is transferred off the wire and into the press section. Here, the fragile wet paper is sandwiched between thick, porous belts of synthetic felt. Supported by these absorbent blankets, the paper is fed through a series of massive heavy rollers, known as press nips. The rollers are typically made of dense rubber and polished steel, and they are pushed together with immense hydraulic force. As the paper passes through the nip, the intense pressure literally squeezes the water out of the microscopic spaces between the fibers. The water is forced into the synthetic felt, which acts as a dynamic sponge, carrying the moisture away before being continuously vacuumed clean. The engineering tolerances in the press section are staggering. The rollers must be perfectly cylindrical, but because they are so long, they naturally sag in the middle, under their own immense weight. To counteract this, the steel rollers are often crowned, meaning they are machined slightly thicker in the center than at the edges. When hydraulic pressure is applied, the roller bends perfectly flat, creating a uniform, perfectly even pressure profile across the entire 30-foot width of the paper. Despite the massive pressure, the paper exiting the press section is still roughly 50% water. It is now strong enough to support its own weight and enters the longest part of the machine, the dryer section. The paper web snakes its way over and under dozens of massive hollow cast iron cylinders. High-pressure steam is continuously injected into the center of these cylinders, heating their outer surfaces to hundreds of degrees. As the wet paper contacts the hot iron, the remaining water begins to aggressively evaporate. The temperature profile of the dryer section is carefully graded. If the first few cylinders are too hot, the water inside the paper turns to steam too rapidly. The sudden expansion of steam gas within the fiber matrix would literally blow the sheet apart, a failure known as blistering. Instead, the heat ramps up gradually, drawing the moisture out gently. It is within the dryer section that the true magic of papermaking occurs. As the water evaporates from between the highly refined, frayed cellulose fibers, a powerful physical phenomenon takes over. Surface tension and capillary forces draw the microscopic fibrils closer and closer together as the water layer shrinks. Eventually, the water completely disappears, bringing the outer walls of adjacent cellulose molecules into extremely close proximity, so close that the oxygen and hydrogen atoms on the different fibers begin to share electrons. This forms a vast network of hydrogen bonds. No artificial glue or binder is needed to hold paper together. The mechanical fibrillation, followed by the thermal removal of water, forces the fibers to chemically lock themselves into a unified matrix. This hydrogen bonding is the fundamental working principle of paper. It is what gives the sheet its impressive tensile strength and unique flexibility. Once completely dry, the paper is strong, but its surface is highly porous, acting much like a paper towel. If you tried to write on this raw paper, the liquid ink would immediately wick into the microscopic gaps between the fibers, spreading wildly and bleeding through to the other side. To solve this, the continuous sheet passes through a size press. This machine floods the surface of the paper with a thin solution of liquid starch. The paper then passes through a set of rollers that press the starch deep into the outer layer of the fibers. The starch acts as a microscopic sealant, filling in the pores and coating the exposed cellulose. After passing through a brief secondary dryer section to remove the water introduced by the liquid starch, the surface of the paper is locked. When you later write on this sized paper with a pen, the ink is drawn into the sheet by capillary action, but its lateral spread is aggressively halted by the starch barrier, resulting in crisp, clean lines. For high-quality printing papers, a specialized mineral coating is applied next. A thick slurry made of ultra-fine calcium carbonate, or kaolin clay, mixed with synthetic binders is pumped onto the paper. Immediately after application, a flexible razor-sharp steel blade presses against the sheet. The blade scrapes off almost all the coating, leaving a microscopic, perfectly smooth film that fills in every valley and crevice between the surface fibers. This blade actually rides on a hydrodynamic wedge of fluid coating, never touching the raw paper beneath. Infrared heaters instantly flash off the moisture, locking the mineral layer in place. To give the paper its final perfectly smooth finish, It is fed into a towering machine called the calendar stack. This consists of multiple vertically stacked rollers made of highly polished, chilled cast iron. As the paper weaves through the stack, the combined weight of the heavy rollers generates extreme compressive forces. This compression flattens the highest microscopic peaks of the cellulose fibers and aligns the mineral coating particles parallel to the surface. The slight slipping action between the rollers generates intense friction, physically glazing the paper, giving it a uniform thickness and a highly reflective, glossy finish. Finally, the continuous miles-long web of finished paper reaches the reel. Traveling at blistering speeds, the paper is wound around a massive steel spool. Just before it is wound, the sheet passes through an advanced computerized scanner. This traversing sensor head sweeps back and forth across the flying web. It utilizes beta particle radiation and advanced lasers to measure the exact basis weight, thickness, and moisture content of the paper hundreds of times a second. If the scanner detects that the paper is a fraction of a micron too thick on the left side, it sends a digital signal all the way back to the head box slice lip, triggering a microscopic thermal actuator that narrows the slit in that exact zone, reducing the pulp flow in real time. Once the massive jumbo roll is full, containing over 20 tons of continuous paper, it is lifted onto a winder for slitting. Rotary shear knives, acting exactly like continuous pairs of scissors, slice the wide web into narrower, manageable rolls. The top and bottom circular blades must be kept incredibly sharp and precisely aligned. If they dull even slightly, they will crush the paper rather than slice it, creating microscopic edge fractures and releasing clouds of cellulose dust that will later clog commercial printing presses. The winding tension is precisely controlled, winding the paper tightly around the inner core and gradually loosening toward the outside diameter, ensuring the massive rolls do not telescope or collapse inward under their own immense pressure. Understanding how paper is made reveals exactly how paper works as a physical object. The strength of a sheet of paper relies entirely on the integrity of its hydrogen-bonded network. When you fold a piece of paper, you are physically bending the rigid cellulose fibers and stretching the hydrogen bonds on the outer radius of the crease. If you fold it back and forth repeatedly, you induce severe mechanical fatigue. The rigid fibers eventually snap, and the microscopic bonds permanently fail, causing the paper to easily tear along the weakened line. When you tear paper normally, you are not actually breaking the strong cellulose fibers themselves. You are forcing the hydrogen bonds between them to let go. The fibers pull away from one another, which is why a torn edge of paper looks fuzzy and frayed under close inspection. You are seeing the naked, unbonded fibrils sticking out into the air. Furthermore, the physics of paper are intimately tied to moisture. Because the entire structural integrity of the sheet is based on hydrogen bonding, paper is inherently sensitive to water. If a sheet of paper becomes wet, water molecules flood into the microscopic spaces between the fibers. Because water is an extremely polar molecule, it aggressively inserts itself between the cellulose molecules. The strong fiber-to-fiber hydrogen bonds are instantly replaced by much weaker fiber-to-water bonds. Deprived of its structural locking mechanism, the intricate network rapidly falls apart, and the strong, flexible sheet reverts back into a soft, mushy pile of disconnected fibers. Every property of paper, from its crisp snap and smooth texture to its ability to hold vivid ink and support massive tensile loads, is a direct result of meticulously aligning organic fibers, treating them chemically, destroying their natural shape, and using the fundamental forces of water and heat to bind them back together in a perfect, uniform plane.